video, we have covered the change in temperature, right, which corresponds to the kinetic energy of the particles. Now we're going to talk about the what affects the potential energy of the particles itself, which is actually the state of matter itself. So the thing is, you can think of your change in temperature and change of state as they are exclusive, which means you can only have one happening at the time. So which means if I change state, I can only transfer energy without any change in temperature, which means my kinetic energy remains constant. Okay, so maybe we can just jot it down over here that your Ke of particles remain constant. Okay, so only the potential energy increase. So it's either potential energy of the particles increase or the kinetic energy of the particles increase. Okay, so basically I am still gaining heat, but whether I allocate it to kinetic energy or whether I allocate it to potential energy really depends on, am I changing state or am I just changing temperature itself? So for solid to liquid, we know melting and solidification, vice versa, liquid to gas, boiling and condensation itself. Now, we do know that in chemistry or in lower set, you have learned, for example, sublimation and deposition itself. Typically, unless it's a database question or information is given to you, typically those aren't tested in your syllabus itself. Okay, but for IP schools, I'm not sure to what extent that your schools will cover, so do take note about this. But generally, if you know that you're changing from a less energetic state to a more energetic state, you can actually see that usually the explanation is exactly the same. Okay, so now this one, the thing is, you need to memorize both versions. Okay, why? Because I have students who have just only memorized the melting and boiling one where you become more energetic, right? But when it flips it around, when the question asks about the cooling version, solidification and condensation, they are unable to flip the words accordingly. Because if you notice, the first line is energy is actually absorbed, right? To overcome your forces of attraction. And if you want, you can actually add in words here to change state. Okay, so you add in here to change state. What happens is you will notice that the observation is that the potential energy of the particles increase because the spacing between them increases while the kinetic energy remains constant. Therefore, temperature is also constant. So you can see basically the general idea is I am absorbing or gaining heat itself just to overcome my force of attraction. And first thing, remember, I'll allocate it the potential energy so that I can change state. And my kinetic energy, I do not allocate any of the heat gain to them. So that it will remain constant and therefore my temperature is constant. So for example, water, if I'm boiling at 100 degrees Celsius itself, I will keep boiling at 100 degrees until all the water becomes steam. Okay, now for the other part, the negative part, right, energy is now released to actually form stronger intermolecular force of attraction. Same thing is to change state. Okay, then likewise your potential energy actually decreases. The spacing between, oh sorry, there's a typo here, can you all change this? This one should be decrease. Okay, there's a typo in the words. Okay, while the kinetic energy itself remain constant. Now, do take note, when we talk about kinetic energy, oh sorry, I used the wrong color. So when we talk about your kinetic energy or your potential energy in this chapter itself, please make sure that you always add in the word of the particles, of the particles, of the particles. Because if you don't write of the particles itself, you are not referring to internal energy. The word internal basically means of the particles itself. So you actually need to include it so that you will actually have the proper phrasing itself. Okay, so just write the whole chunk down. Usually when they ask you to explain why temperature remains constant when there's a change in state, just write the whole thing down. Okay, which means this fellas is your standard answer. Okay, so I have to just memorize it. Next, we're going to talk about a very unique change in state, because normally if you notice the change in state that we have here, temperature is always constant, right? However, evaporation is not the case. It's the only change in state that temperature changes. More specifically, decreases. Okay, so it's a bit special for this fella here. So evaporation itself, what is evaporation? Like define evaporation, right? Evaporation is basically the phenomenal or basically a situation where liquid particles at the surface gain enough energy. Now, how do they gain the energy itself? It's actually from the particle theory, because remember, your liquid particles are in constant random motion, right? And because they're in constant random motion itself, it is possible that at certain point in time, there could be some particles that have more energy than the rest. So because of this, they can actually overcome their intermolecular force of attraction, and number one, they must escape successfully. If they don't escape successfully itself, basically what's the point? They can't escape as gas, they remain as a liquid. So you can see this part is actually linked to this. Oops, sorry. Okay, this part is linked to this. So do take note, what happens during evaporation is that all the energetic particles escape, right? What happens is that, why do we need to talk about it being successful? Because the successful part is over here. Why do we need to be successful? Because if some of the liquid particles escape as gas, but they bump into other liquids, okay, so if they bump into other liquids, other gases in the air, there's a small little chance that they will actually bounce back into the liquid itself. So if they don't escape successfully as a gas particle, we don't say that it evaporated. For you to evaporate, you must escape and escape successfully. So what's the problem is now, whoever is left behind are all the less energetic one. So more energy escape, your less energetic are behind. So this is the reason why temperature decreases, because the less energetic is left behind, average kinetic energy decreases. Okay, so because of that, just be careful, because at the surface, more energetic overcome, escape successful. Okay, so this here is why does evaporation cause temperature to decrease. Okay, so this is the reason why your evaporation will cause temperature to drop. So when temperature drop is because all the highly energetic one, you can think of them as they are the one with a lot more energy, a lot more heat, and if they escape, all those that is left behind got less heat, and therefore they will actually be lower temperature. They have lesser average kinetic energy itself. Okay, so you can see over here there's a difference between boiling and evaporation, so you need to at least know three differences. You need to at least know at least three of them. Okay, so the most straightforward one is bubbles. Bubbles are formed, no bubbles are formed. Okay, and it occurs throughout the liquid, that's why you actually see bubbles. So technically these two are actually very similar, and basically I need an external source. This one don't need external source. Okay, so do take note about this. And your rate of evaporation, if you remember, right, rate of evaporation itself, number one, I must be at the surface, I need to have enough energy, and I need to escape successfully. So if you were to notice, let me just write down, this is talking about the surface, this is talking about the escape successful, this is talking about the energy needed. Okay, so if that is the case, you can actually try, if you are very familiar with the definition of evaporation itself, you'll actually be able to explain why, or link it directly to the reason why you actually will have all your factors, how does it affect your evaporation itself. Okay, so let's go through in detail a bit. When you have a larger exposed surface area itself, which means there are more liquids at the surface of the liquid. Therefore, it is more likely that the liquids at the surface have a higher chance of having more energy and being able to overcome their force of attraction to escape successfully as a gas particle. On the other hand, if you have greater movement of air or wind itself, basically if you escape, just imagine you're a liquid particle, you escape into the air and then the wind blows you away, you escape successfully. It's like a bank heist where they have a car ready and then the robbers, they just see the car and go away, and increases the chance of them escaping itself, right? And lower humidity itself. Now, humidity basically means the amount of water droplets in the air. So if there's less water droplets in the air, if my liquid evaporates and escape, there is less particles trying to block me, I can escape more successfully. And for your lower air pressure itself, it's the same thing itself. When you have low air pressure, I have lesser air molecules. So because I have lesser air molecules, it's the same reason as the low humidity one, I can escape more successfully. Now for the higher temperature itself basically means the average kinetic energy of my particles are higher. So it is more likely that I have enough energy that I can actually escape from the surface itself and overcome the force of attraction. For low boiling point itself, basically this is talking about the strength of your IMF, your intermolecular force of attraction. So if your force of attractions are weaker, it's easier for you to break away and overcome and escape as a gas. Okay? Now, let's take a look at the word example. State the difference between boiling and evaporation itself. Boiling requires an external heat source, while evaporation does not. Bubbles can be observed during boiling throughout the liquid, while bubbles are not seen during evaporation. That's it. Okay, so you just need two answers, two comparisons. Why? It's just a 2-mark question, 1 mark for each comparison. Okay, so because of this, you can actually just use any of these two to talk about it as well. Okay, but generally use the one that comes to you more straightforward, which one comes to you more naturally itself, because ultimately this is what I'm more familiar with. You should choose the one that you yourself is more familiar with, so that it's easier for you to solve and target the questions itself. Okay, now in terms of kinetic particle model of matter, why does the rate of evaporation increase when it's heated? When the liquid is heated, its temperature increases as the average kinetic energy of the liquid particles increase. It is more likely for the liquid particles at the surface to have enough energy to overcome the intermolecular forces of attraction and escape successfully as gas particles. Okay, so basically you have this part all together. So you just want to link the temperature, kinetic energy, you can overcome it and escape. So directly, what's the factor? Temperature increase. So explanation for the elaboration for the explanation itself. So point, elaboration, answer. Okay, now when the exposed surface area of the liquid increases, there are more liquid particles at the surface. It is more likely for the particles at the surface to have enough energy to overcome their the molecular forces of attraction and escape as successfully as gas particles. Okay, because basically it is talking about chance. What's the likelihood of it happening itself? So the more surface area you have, the more liquid particles you have. The more liquid particles you have, it's more likely for you to happen. Therefore, you have all of this that happens. Okay. So just now we have been talking about all the change in state. You see, all of this is explanation, 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 right? So a very, very lengthy chapter itself. So if you are not very familiar with the chapter of heat, you have to really sit down and put in effort to go and memorize a lot of the content. And as well as later on, we still need to focus on your calculation parts. Okay, so moving on to the calculation part. So if you recall at the very start itself, we do mention that when we talk about change in state, if you want to calculate, we need to use latent heat and specific latent heat. Okay, so let's talk about what these two definitions are. Now, latent heat, right, basically is just the amount of heat that you use to change state. Okay, then if you talk about latent heat of fusion, we're talking about melting and solidification. If you're talking about your vaporization, it's talking about both boiling, condensation, and also evaporation as well. Now, the one that we use more commonly itself would be your specific latent heat. So same thing before, if you see the specific itself, it just means per unit mass. So unit per unit mass itself is basically just latent heat divided by mass, which is just Q over M. The formula that we use is Q equals to ml most of the time. However, if you're looking for definition wise, if you're explaining in terms of definition, we are talking about specific latent heat, which is L is Q over M. So you can see, right, the keyword is the L, latent heat. Okay, so some students get confused with your specific heat capacity and your specific latent heat. They are very, very different things. Specific capacity is for change in temperature. Specific latent heat is change in state. Okay, and likewise, I always tell you guys, whenever you use a formula, make sure to use SI units. Okay, so you can see all the different definition itself. What's the breakdown? You can see that basically it's the same, but if you have the word specific, it is of 1 kg of the substance itself. Okay, then let's talk about your calculations. Okay, now let's talk about the amount of energy. So energy is Q already. All right, you want to melt this amount of mass at constant temperature, and they give you specific latent heat. This is L. So we have L, we just use Q equals to ml itself. What's M? 100. Now, to be careful, always need to double check whether it is what values they give you. So 268, and because kilo, I will change it to 1000. So you end up with a very, very big number itself. Press your calculator just to make sure that you got it correct. 268, 123. You should have 26,800,000 joules. Okay, and if you want to standard form it, perfectly fine as well. If you want to use kilojoules, also fine. Alright, next, same thing, energy, mass, specific latent heat. So actually the same formula itself. This one is just to familiarize yourself with the formula 1.2, 193, 123. Okay, press the calculator as well. 1.2, 193, 123. Okay, let me just write it nicer. Okay, so you should end up with 231,600, and we'll round it up to 3 SF. 3 joules, 3 SF. Okay, if your school use 2 SF or the smallest SF, just use them accordingly.